Hello everyone, welcome to our video explanation of our practice problem with a clock. Let's say the minute hand of a standard circular clock has a length of 0.12 meters. Using the knowledge of clock hands, projection of uniform circular motion as simple harmonic motion, and the given information on the length of the minute hand, find the amplitude of the motion if it was projected onto a single x-axis when viewed from above, simple harmonic motion, the period of the motion, the frequency of the motion, and finally, the position equation x of t that would represent the object's simple harmonic motion. Okay, well, let's break this problem down. Here we have this clock, and it has a minute hand that is going to rotate about our clock with a length of 0.12 meters. Well, if we view this clock from above, here's our position at above at 12. Whenever this end right here is rotating clockwise and gets to 3, it is going to be right here. And then it goes back to 6, so it's going to move back over here. And as it gets to 9, it's going to once again go to the other side and come back at 12. Well, whenever in simple harmonic motion, the amplitude is the maximum displacement from equilibrium. If our equilibrium or our center is at 12, then we know that our amplitude is going to be at 3. And because this right here resembles the radius of a circle, we can determine that the length of our minute hand, which is the radius of the minute hand's circular motion, is going to be our amplitude. So in essence, this means that if our radius is equal to 0.12 meters, that same radius, whenever the minute hand rotates to 3, is going to be our amplitude. So our amplitude is going to be 0.12 meters. A is equal to 0.12 meters. Now how about the period of the motion? Okay, so we know that the minute hand of a clock makes one full rotation about the clock in an hour. And because this rotation is one full cycle, as you can see, it's one full cycle because it's making one full circular motion around the clock. It's going to go here. This is how we would view it in uniform circular motion. And in simple harmonic motion, it's going to go here, here, and once again back to the center. So that is going to be our period. And because we know that the period of a minute hand rotating around a clock is 1 hour, and 1 hour is equal to 60 minutes, we can use dimensional analysis to find that 60 minutes, when multiplied by 60 seconds per minute, is going to give us a period of 3,600 seconds. Now for our frequency, we know that frequency is inversely proportional to period. So we could say that frequency is equal to 1 over big T. Frequency is equal to 1 over big T. If our period is 3,600, our frequency is equal to 1 over 3,600 seconds, which will give us about 2.78 times 10 to the negative 4 hertz. Now, how do we know that this is hertz? Well, if we look back over here in our frequency equation, we could see that we have 1 over 3,600, which is going to give us this number, and we have 1 over seconds. Well, 1 over seconds is basically what hertz is, because hertz is just 1 over seconds. So we know our unit for frequency is going to be hertz. Okay, now finally, how do we find the position equation for harmonic motion? Okay, well, our raw position equation is x of t is equal to a cosine 2 pi ft. Okay, well, we already know our amplitude is 0.12 cosine, and then 2 pi frequency time. Well, over here we have this really difficult number to write for frequency, but because we know frequency is also 1 over period, we could say that this can instead be written as 2 pi t over period. So it'll be cosine 2 pi, and then 2 pi t over 3,600, which gives us the final equation for our position over time for our simple harmonic motion.